All right. Just one thing to finish up from last week. Okay, we were looking at multi-threading, which involved the thread class and the runnable interface. And the book offers, it's true that there are two options. One is to subclass thread, and the other is to implement runnable. Yeah, implementing runnable is the only way to go, just because subclassing thread kind of locks you into that class hierarchy with pretty much no benefit. So when you write a class, implement the runnable, and then two ways to execute. You take the runnable, instantiate a thread object passing the runnable to it, and then you invoke start. And the tricky thing about that is what start does is it starts the thread calling the run method in your runnable, but then continues execution. That's the, if you remember in the example, the very last line was say we're all finished, but that got printed before anything else did. You know why? Because it just buzzed right past the start methods and executed that. So one way to kind of say, all right, I want to wait till they're all done is using the join. And there were examples of this. We showed that. But really, the way to go on this is using an executor. And my experience on this is I always use a fixed thread pool. The cache thread pool is a bit risky, because if you create because in my usages there've sometimes literally been thousands of independent threads running, and that'll just kind of grind everything to a halt. So instead, what I do is actually in the applications I have in mind is what I will typically do is I'll inquire as to how many logical cores there are on the computer, and then create that many threads. And what I found is that maximizes the execution, because each the thread scheduler in the virtual machine tends to schedule each of the threads in a separate core if it can. And so what that means is that each core just has one thread that's competing for its resources, apart from other things that are running. And I found that sort of optimizes the execution. And what that allows you to do, especially in our multi-CPU environment, is to just have significantly better execution, as long as you can kind of parallelize it. There are lots of issues where you can take a program, make it multi-threaded, where things are kind of coming in and out of the same objects methods, and there's things involving synchronization and making sure that you don't get, it's really a tightrope you have to walk there, where you have multiple threads changing things all at once when they shouldn't, and then you prevent that, and then you create something called deadlock, where the program just kind of locks up, where it's like, one thread is waiting for something, and the other thread is waiting for something else, and then they just kind of have a standoff. So that's, we're not delving into that. I mean, if just kind of know that that's something that's an issue. So, yeah, and then we have this terribly named shutdown, which is it's an important method. What it does is it signals the executor that there are no more threads going to be sent to it. Yeah, and actually the executor keeps. I kind of misspoke that. You give the executor the runnable, and what it does is it keeps a thread pool, a pool of these threads, and has as they finish, it takes the next runnable and kind of pops it in, and then only exits when things are done. Like the start method, it kind of buzzes past that, and so if you want to make sure that things kind of block until all of the threads are finished, then you have this await termination, which is a better name thing, which means wait for everything to be finished. Okay, so that's where we were. Now, the last little bit on this, and this is how should I say, what I'm trying, one of my filters in terms of what I'm presenting, especially when I am talking about things beyond what the book has, are things that I have found useful in the programs that I've written, and this is one of them, where the situation is an application where the problem with the run method is that its return is void. In other words, if you want to get information on what happened, you have to start kind of querying the object, and that can, it's possible, but it's a little bit tricky. In a lot of cases, you want to kind of have a return, and that return can be anything from just sort of a Boolean that says, okay, things worked well, to actually more complex things. Just in one of the models for NavSup, what they wanted was because they were installing this in their system, what they wanted is they wanted a JSON file that had information about what the input was, information about how the run went, and any error messages about whether it was a success or failure, things like that. All of it, all in a JSON file. So basically, I wrote a callable where the return was one of these JSON objects. So the return, notice that the callable is a generic, which means I can any class whatsoever you can kind of put there. So just for a very simple example, I did a little thing called random callable. Again, it's not an exciting thing, but it just as an example. Actually, I think I misspoke there. That should be a callable integer. Anyway, so how do you get these things? And then you get them using these future objects. And so what you do is you submit these callables to an executor service, just as you do with the runnable things. But then the future can invoke the get method on the callable to get the stuff. So what does that look like? Okay, so this random callable, it implements the callable with an integer. It sleeps for a random amount of time, and then returns the amount of time it slept. So it's giving you information about kind of something that went on the inside. Again, not a terribly exciting thing, but it should give you some idea about if your callable, the call method does something, so the call method is like what run would do, and then okay, so let's look at what do you right here? Okay, so here's the class. So it implements callable with an integer. Again, this is just like when we were doing collections and maps. You say, okay, if I have a set, it's going to contain an integer, or a set's going to contain a string, or a set can contain a playing card. I mean, it can be just about anything. Just to keep track of these things, this sort of next ID and ID thing is this is a pattern that we've seen a couple times. The advantage of this pattern is that it just sort of happens. In other words, the other option is to have the constructor have an argument that's going to be the ID of that thing. That's the other option. So why not do that here? Well, the problem with that is that then this object has no control on whether or not it's gotten two different objects with the same ID. In other words, there's nothing to prevent two instantiations passing at the same ID, and that would cause confusion. With this pattern, we have this static next int and an instance variable, ID. And so the idea is that every time I instantiate one, the instance variable gets set to the static variable, and then the static variable increments. So this automatically, no matter how few or how many of these I create, they will all have a unique ID. So I'll be able to tell them apart. And it's sort of hands off. I don't have to worry about accidentally giving the right one. So the idea is that the upper bound, that's going to be, the call method is a pretty simple one. What I'm doing is I'm just sort of generating a random amount of sleep time based on the upper bound. I'm giving it a minimum of 1. And then I'm using this time unit instead of the thread sleep. The thread sleep has been, it hasn't quite been deprecated, but they complain about it. This time unit actually kind of does the sleep thing in the right way. And so, so here's the call method, and that gets, notice this is part of the interface, the callable interface. And so the return is whatever generic I've given it. I've given it integer, so it's going to return a call. If it was a string, it would return a string. In the case of the application I mentioned with the JSON, it returned a JSON object. So it sleeps for a certain amount of time and then returns, this is how long it slept for. So this is a way of using it. So here I created 10 of them. And I gave it sort of an upper bound of 10 seconds. Okay, so and what did I? And this is something that I found I kind of needed to do because I wanted to keep track of them. So here I have a list of these callables, and array list is just sort of fine. So now I have all of them, and I could have done all this up there, but what I found is I did want to keep these objects around. So this is similar to what I did in that application I was referring to. So now I'm going to have a fixed thread pool with just that number. Okay, now what I want to do is I want to stay. What I've also found is that I need to keep the futures around. Okay, so what I'm going to do is I'm iterating over the callables, and then I'm submitting. And when I submit to an executor, it returns an instance of the future, which I'm now going to just save in this list. So now I have a list of all the futures, and then as each of the callables executes its thing, it's going to put the information into the future. Now the shutdown again. That the very first time I was kind of using this, I thought shutdown meant that the thing would shut down, but it doesn't. That just means no more. And then, okay, we'll wait for all of them. Otherwise, we're just going to kind of, and then now, once they've all been executed, I'm going to just sort of print what each of them are. So the get method from future is what is going to have that value. So when I run this, okay, come on. Okay, now keep in mind that in this case there are 10 of these running, and Okay, so we see it took 9 seconds to run, and these are the times that were generated. And you notice that there was one that was 9 seconds. That's why it took one of them took 9 seconds. There's no getting around that. But the execution time in this particular case is not the sum of them, but it's the maximum of them in this case. Usually since there is some overhead, it would take a little bit longer. Like if I made, let's, just out of curiosity, what if I did 30 of these guys? Now that's probably not going to just take, about 9 seconds, but it's not going to take 30 times 9. Okay, it took 10 seconds. Okay, so there was an extra second of because there's obviously some overhead. So there was 1 second of overhead. There were several, let's see, I see one that was, yes, there were several that took 9 seconds, but they were all operating simultaneously. And since this only has 16 cores, there were multiple threads competing in the same core. That's probably where a lot of this came. One of the reasons why I like to only have one thread per core is that the threads are not competing for each other. What happens is the thread scheduler will execute one thread for a little while and then execute another one, but it takes time to kind of swap them in and out. Okay, so all right, so that's